Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. Today's lesson is the first lesson in the Equilibrium unit, and what we're going to look at is just the fundamentals of equilibrium in terms of what is equilibrium. We'll start with that. What conditions are required for equilibrium? How can I tell a system is at equilibrium? And how can I express which way an equilibrium favors? So let's start with what is equilibrium, and I'm going to start with a couple of really basic equations. So the first equation here, this is the formation of ammonia from its elements, and this equation here is the decomposition of ammonia from its elements. Now let's focus on the first one. Is it possible to take nitrogen and hydrogen and make ammonia? I hope the answer you said was yes. This is how we make fertilizer, and it's a big part of the agricultural world. Now let's think about the second one. Is it possible for NH3 to decompose into its elements? And I hope your answer is yes. It is thermodynamically possible for this to happen. So everybody's fairly comfortable with that. I've got a formation, I've got a decomposition. But how does this tie into equilibrium? Well, what I'm going to do is I'm going to show you what equation number one would look like if I had a reaction vessel. So I'm going to call this thing a reaction vessel. And I'm going to say we're pumping nitrogen gas in here, and we're pumping in hydrogen gas in here, and it's entering into this reaction vessel. So what would happen is it would quickly start to flood with nitrogen gas as well as with hydrogen gas. Okay, so it starts flying into the container, and what will just naturally happen is these things will start smashing into one another. And if they hit with enough energy at the right angle and all the things work out perfect, you will get these two things starting to form NH3 gas. All right, simple enough. Here's my forward reaction. Nitrogen hits hydrogen, it starts to form ammonia gas. Now let's think about it from the other perspective. Now that I have ammonia, aren't ammonias going to hit with one another? They sure are. These ammonias are going to start smacking into one another, and if they hit at the right angle with enough energy, just perfectly, they will actually start to reform nitrogen and hydrogen. This seems really counterproductive. I want to make ammonia, and I am, but at the same time, the ammonia is now reacting and going the reverse direction. That's weird. And guess what? That's equilibrium. This reaction really should not be expressed like number one or number two unless you are specifically really just talking about one of those reactions occurring. In reality, these reactions are happening simultaneously, going opposite directions, and never reaching completion. An equilibrium reaction never gets to an end point. It's always fighting with itself. Reactants making products and products making reactants. And they're doing this at the same rate. Now, how we actually would express this would be like this. I would have nitrogen gas and hydrogen gas, but rather than a single arrow forward, it's an equilibrium arrow. The reaction is going forward and the reaction is going reverse. So this would then make 2 NH3 gas. This thing here is called an equilibrium arrow. And what it represents is that the reaction is both going forwards and reverse, and that they're doing this at the same rate. So imagine that, I'm going to give you an example. Imagine you're watching a hockey game and one team is on the power play and one team is on the penalty kill. So we got 5 players, I'm going to call it on reactant team, and we got 4 players on the product team, okay, the team on defense that is penalty killing. There is an unequal number of players on each team, 5 and 4, but when they go to the bench to change, the rate at which they change is equal. It's 1 player on, 1 player off. So although the particles or players can change in terms of the ratio, 1-to-1, the amount of each on each team is different, which is similar to this scenario here. I have 4 particles of reactants for every 2 particles of products. And the rate at which I make these is equivalent, the rate, but the amount of products and reactants I have doesn't need to be equal. Just like the players on the ice don't need to be equal, they're 5 and 4, but how they change, which is a 1-to-1 ratio, 1 player on, 1 player off, that's the rate at which they change. So equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction, and so the concentration of the products will be constant, the concentration of the reactants would be constant. So I'm going to draw a graph to help explain this as well. So on the y-axis, we are going to put concentration in moles per liter, and we're not going to use any numbers, so this is the y-axis. And on the x-axis, we're going to have time in seconds. So I said that we would start with hydrogen and nitrogen. I'm just going to start with them up here. So I've got a high concentration of my reactants. What would happen is as the hydrogen entered the vessel, it would start to react with nitrogen, and its concentration is going to go down because it's being used up during the formation of ammonia. So I'm going to call this green one hydrogen. And nitrogen would be doing the same thing. So it starts with a high concentration. Its concentration starts to decrease as it reacts with hydrogen because it's being used up to make ammonia. And eventually, it will flatten out. Okay. Now, at the same time, if I'm making ammonia, I start with none, but I rapidly start to make ammonia because there's so much nitrogen and hydrogen, they're going to react a lot. But as the concentration of ammonia increases, it starts to react with itself, reforming hydrogen and nitrogen. And so it's decreasing its own concentration, plus we have less concentration of reactants, so this starts to slow down and eventually flatten out, just like my other lines. Once all of these lines have flattened out, and I know it's not perfect, but it should be the same for all of them. Once they all flatten out, I have reached equilibrium. Because equilibrium is when the rate of the forward reaction and the reverse reaction are equal, and the only way that that's possible is if these concentrations are constant. So if I extend this line, the concentration at this point is not changing. I'm at equilibrium. When I extend this line, this is now at a constant rate, a constant concentration. It's going to be level, and same thing with the ammonia. Okay, so once these lines are flat, I know I am at equilibrium. So the official definition of equilibrium is when the reaction of the rate forward is equal to the reaction rate of the rate reverse. Now, if you're wondering, I know about rates a little bit, like meters per second. What on earth would that be in chemistry? And the answer is it's in moles per liter per second. So concentration is the number of moles per liter, and then the rate is how that concentration changes per second. This is part of a unit called kinetics, which we will not be touching on. And so when the reaction rate forward is equal to the reaction rate reverse, The moles of these substances per liter is changing per second at the same rate that their products are changing in terms of moles per liter for every second. That is the definition of equilibrium. The definition of equilibrium is not when the concentrations of the reactants and products are equal. It's not that we have 50% products, 50% reactants. That can happen, but it's super rare. What it means is the rate at which I'm producing products is equal to the rate at which I'm producing reactants at a certain time interval. Okay, so when you have a bank account in equilibrium, you have money coming out at the same rate as money coming back in. Okay, all right. The next thing we need to know is what are the conditions in order to have equilibrium, and there are only two. A system must be closed, and you have to have both reactants and products present. Now, to quickly review, an open system is when matter and energy can move in and out of the system, both things, particles and energy. A closed system is when energy can move in and out, but matter or particles cannot. Okay, so for instance, again, imagine I would have to have a reaction vessel, and this would have to be sealed, but I could, if I wanted to, I could heat it up, put a flame underneath it, a Bunsen burner. I could heat it up, or I could put it in a cold water bath. I could cool it down. So energy can move in and out, but it's a sealed container. Nothing can, no particles can move in and out. And then the other one is simply you have to have reactants and products present. So our example of something called the Haber process, which is this one, is in equilibrium. Okay, so this is in equilibrium. But an example of something that would not be in equilibrium, well, if I combusted methane, I don't think the carbon dioxide and water would reform methane. If that was true, we would have no energy crisis. We would still have, global warming crisis. So this is not in equilibrium. It has a single arrow forward, whereas this is in equilibrium, and it means you have both reactants and products present. So that's it for conditions. Let's look at the next thing, which is, how do I even know I am at equilibrium? So we use macroscopic properties. So macro means big, right? Macroeconomics, big economics, microeconomics, looking at something much smaller. Okay, and we generally do everything in terms of gases or solutions in this course. So I have an example over here of a gaseous system which can be in equilibrium. Now, I could do a number of qualitative things and even quantitative things to check to see if this was in equilibrium. Okay, so the first thing I could do, I could check for the color of this system. So again, I'm going to have you imagine I have a vessel, it's clear, it's glass, and inside of this vessel I have dinitrogen tetroxide, and nitrogen dioxide. So essentially what these things are doing is they're bouncing around this container. Now, if this is colorless and this is brown, and if the concentration of what is brown is unchanging, and if what the concentration which is colorless is not changing, then when I look in here, it's going to be some shade of brown or orange. If the amount of what is brown is constant, and what is colorless is constant, the net shading of this is going to be consistently brownish, okay? But if the forward reaction was happening at a faster rate than the reverse reaction, I would be producing what is brown at a quicker rate, and this would start to look more and more and darker and darker and darker brown. Or conversely, if the reverse reaction was happening at a faster rate than the forward, then what would happen is what is brown would get turned into something which is colorless. And so this would start to become less and less brown, more and more orange, and then maybe eventually almost completely colorless. So I can use color to do that. The other thing I could use is pressure. Okay, so I'm going to draw an imaginary pressure gauge. Okay, so it's a circle. Pressure gauges usually have a needle, and then they move up as there's more and more pressure. So imagine I have a pressure gauge. It's up here. My pressure gauge is on there. Okay. If the pressure is unchanging, let's say 100 kilopascals, then I must have a consistently even amount of particles. So in order to have a consistent amount of particles, the rate in which I form this has to be equal to the rate in which I form this. The concentration of these particles have to be held constant, which is what equilibrium is. The concentrations of reactants and products are held constant. However, if this reaction was going faster this way, I would be turning one particle of gas into two. And if I got two more particles of gas, then the pressure would go up. So if this reaction was happening faster forward than it was reverse, I would be making more particles. I know this because of the coefficient. I got two particles, and my pressure would start moving up. Okay. Conversely, if I had a reverse rate which was faster, I would be turning two particles into one particle, less particles, less pressure, and the pressure gauge would be going down. But if I was consistently a constant concentration here and concentration here, then the number of particles would be unchanging and the pressure would be constant. So I'm looking for, so far, a color which is constant and a pressure which is constant. Okay, I could also use temperature. So for instance, this is a endothermic reaction. Okay. Now, if the forward and rate reactions are equal, it's producing heat and consuming heat at an equal rate. And so a temperature gauge wouldn't change. So imagine I had a digital temperature gauge. Okay, and it said, I don't know, 34 degrees Celsius. Okay, if I'm consuming heat at the same rate as I'm producing heat, this will stay constant. But if the forward reaction goes faster, then I'm consuming more energy than I'm releasing, and this will start to go down. It'll be 24, 23, 13, etc. Conversely, if the reverse reaction is happening really fast, then I'm releasing heat at a faster rate than consuming it, and this is going to go up. So I can use color, pressure, and temperature for gas equilibriums to figure out whether it's at equilibrium or not. For solutions, the two most common things to use are color and pH. And so I'm not going to go in as much detail here as I did on the previous question, but essentially, if I'm at equilibrium, what is orange, which is this? I'm going to add that in. This is orange. And what is yellow? This is yellow. If the color mixture of those two is consistent, it's at equilibrium. But if it's becoming more orange, this is going faster. Or if it's becoming more yellow, the forward reaction is going faster. And therefore, it's not at equilibrium. Or I could use pH. This is an acidic solution. So if I measure the pH and it's consistently at, say, 1 or 2, and it's unchanging, I'm at equilibrium. But if I'm measuring the pH and the pH is going down, it's becoming more acidic, then I know the forward reaction is going faster because I'm creating more acid than I'm consuming it. And so the pH goes down and down and down. Conversely, if I'm monitoring the pH and it keeps going up towards 7, I must be consuming the acid at a faster rate than I'm producing it, and therefore the reaction is not at equilibrium. So, in summary, equilibrium is when the rate of the concentration of the products is constant and the rate of the concentration of the reactants is constant, and they are unchanging. The reaction hasn't stopped, it's just at equilibrium. The conditions I need to have is a closed system which allows energy to move in and out but not matter, and I have to have reactants and products present. A good example of something which is never in equilibrium is a combustion reaction because it only goes one direction. And I can use color, pressure, and temperature to check to see if a gas system is at equilibrium. And I can use color and pH to check to see if a solution is at equilibrium. So what we're going to look at next is equilibrium expressions and the meaning of a K value. I'm going to first just briefly explain what an equilibrium expression is. It's simply a ratio of concentrations, and it's the ratio of products to reactants. And if you calculate that ratio of products to reactants, what you end up with is a K value. And a K value is simply a number, and it represents that ratio. So let's say I had a K value of 5. What it really means is I have 5 times as many products as I do reactants, because the ratio is always the number of products compared to the number of reactants. Or if I had a value like K is equal to 0.1, okay? Well, what that would mean is really a 1/10 ratio, where the total amount of reactants is about 1/10 the amount of products. Now, I know I did that really quick, so what we're going to do is we're going to look at equilibrium expressions and K values here separately, and we're going to do it one at a time in a lot of detail. So I'm going to start with the equilibrium expression. Again, what an equilibrium expression is depicting a ratio between the concentrations of the products and the concentration of the reactants. So you would get this equation from your balanced chemical reaction, and I have below here a really simple one, A plus B in equilibrium with C plus D. And they would have to be balanced, so I'm just going to use lowercase letters to represent the coefficients. So A would be the coefficient on A, B on B, so on and so forth. Okay, so the pink letters represent coefficients. And I would always be writing these K expressions in terms of products divided by reactants, and these would be concentrations, so we use square brackets. And they would be raised to the power of their coefficient, okay? So whatever that might be. So if I write the expression for this one, what it would be is products over reactant concentrations. So my products are capital C and capital D, and their coefficients would be their lowercase letter, so C and D. And that's all over the concentration of reactants, so A and B, and those would be raised to their coefficients, A and B. Now, if I input numbers into this and get values coming out, I then understand whether products are favored or reactants are favored, which is what we're about to get to, so I'm going to wait a little bit. Now, something I do want to talk about before we get to using numbers, or even any more in depth with that, is how do I know what can and cannot go into this expression? Okay, so it's really important that you understand at this level of chemistry, we are only going to be doing homogeneous equilibrium systems. which essentially means everything must have the same state. So they all have to be aqueous, or they all have to be gases, or they all have to be liquids, or they all have to be solids, etc. And if you have an odd guy out, it has to be removed. So if you have 3 liquids and a gas, you would remove the gas. Okay, so make sure that you remove anything that is an odd guy out state. It's got to be a homogeneous mixture, and if you take chemistry at a higher level, you will do non-homogeneous mixtures. So let's do a practice here. Here's an actual equilibrium system. This is a very famous one. What the first thing we're going to do is we're going to write what the expression is, and then we're going to look at what does the K value mean. Okay, so for instance, K is got to be equal to the products. So my product is NO2 raised to the power of its coefficient, which is 2. And then that is going to be divided by the concentration of my reactant raised to the power of its coefficient, which is just 1, so I'm not going to put it in there. So let's think about this. What does this expression mean? It is the concentration of the products divided by the concentration of the reactants raised to their coefficient. So essentially, if I get a number here and its value is greater than 1, if its value was greater than 1, then I would have to have more products or a bigger numerator than I have denominator. If this was 1 over 1, well then it would be 1. But for instance, this K value is 5. So I have to have, in total, when this calculation is done, a ratio of 5 over 1 to give me this K value of 5. So anything essentially greater than 1 means that it favors the products, and you have more products than reactants. Conversely, let's imagine you had a value that was smaller than 1. If I've got a value smaller than 1, that means my numerator has to be smaller than my denominator. Now, if my numerator represents products, that means I have less products than I have reactants, which is on my denominator. To get a value smaller than 1, your denominator has to be bigger. So essentially what this means is that this reaction favors the reactants, and that means that when I am at equilibrium, I have more reactants than I have products. If my K value is greater than 1, like in this example, it means at equilibrium, I have more products than reactants. Now, if you're a bit confused, you said, but I think they're supposed to be equal. Aren't they supposed to be equal? My answer to you is this. It's not the concentrations that are equal to one another. It's the fact that the concentrations are unchanging during the reaction. I do not need to have the same number of products as I have reactants. I just have to be creating products at the same rate at which I'm producing reactants. Just like when I had the 2 different teams in hockey, I had 5 players on one and 4 players on the ice on the other, but the rate at which they're changing, 1 player to 1 player, is constant, and so they have a constant K value, if that makes sense. Okay, what we're going to do next is we're just going to practice writing these expressions here, and then we'll dive a little bit further into the actual value of K after that. So what I would like you to do now is to try to write an equilibrium expression for this reaction. Make sure that you cross out any states that don't fit. Make sure you have products over reactants, and make sure they are raised to their coefficient. Pause the video now and give the question a try. Now that you've had an opportunity to give the question a try, I'll show you how I would do it. The first thing I would do is I'd highlight all of my states. I would then cross out any odd ones that don't belong. So CCl4 is a liquid. This would not be part of my equilibrium expression. The next thing I would do is I would either underline or highlight coefficients because I'm going to double check that I've used them when I write my expression. So I'm going to write K, or you can also write Kc because this is about concentrations, is equal to my products. Now my products is CCl2F2, and I'm using square brackets to represent concentrations, raised to the power of 1, I'm not going to write the 1 in, times, not plus, because this is the product of, times, not plus, the concentration of HCl raised to the power of its coefficient. Then that is divided by my reactants, the ones that matter, so the gas, the concentration of HF raised to the power of its coefficient. So I hope you did well on that. This would be correct. Great job. I'd like you to try the next one. Same thing. Try to write the equilibrium expression for this reaction. Pause the video now and then check to see if you get it right. All right, this is how I would do it. I would highlight all of the states. Cross out the one that doesn't belong. Keep everything else. Underline the coefficients or highlight the coefficients a different color. There's no coefficient, which means it's 1 each. Then I would simply write K is equal to products. This is CO2 raised to the power of its coefficient, which is 1. No need to put that in. All over the concentration of O2 raised to the power of its coefficient. It doesn't have one, so that's 1. And that's it. So whether you write K or Kc, that's totally fine. The last part of this lesson, we are going to look at, again, what the value of K means. And we're going to look at how you can express it in different ways. And we're just going to tie that up with a couple of simple questions. So when you write out an expression and say you know the concentrations and you put them into the expression and calculate an answer, your answer is really going to fall under one of 3 places. Your K is either going to be greater than 1, your K is going to be dead equal to 1, very rare, or your K is going to be less than 1. So for instance, if my K is greater than 1, I might have something like a value of 3,400. If my K is equal to 1, it really means it's equal to 1. Or I could have my K being less than 1, and I could have something like, for example, 5 times 10 to the negative 2. Okay, so that's one way of expressing it. The other way of expressing it is we can say if something is favored or something is not favored. So in order to have a K value greater than 1, you must have more products than you have reactants. So we often would say that we favor the products, which simply means you have more products than reactants. Again, that has to be possible because if I have products over reactants, the only way I can get a value over 1 is if the numerator is a bigger value. And the numerator value represents the amount of products you have. So obviously I must favor products. If K is equal to 1, then there is no favorability. It's equal. And if K is less than 1, we would say that the reaction favors the reactants. Now another way of showing this is saying which one you have greater amount of. So you could always say something like the products are greater than the amount of reactants. Or I could say the products are equal to the amount of reactants. Or I could say that the reactants have a greater concentration than the products. So that's another way. And the last way we could do it is using a greater than or less than sign over an equilibrium arrow. So for instance, let's say you had A and it was turning into B, and I wanted to say whether this favored the reactants or products. I could talk about it in terms of 50% more or less, okay? So I could write something like this. The reaction is greater than 50% forward, which is telling me my products are favored. Now, I always struggled with greater than, less than signs when there's nothing on the other side. So again, let me explain what's on the other side of that below here. So what this means is the reaction is going greater than 50% forward. So I have more products than reactants. Or if I'm wondering again, how do I get this greater than or less than sign? All I do is I turn that into a little arrowhead. So I go like this. Oh, this reaction is going more forward than it is reverse. Isn't that a neat idea? So what I'll do is I'll put that down here. What you can do, take your arrow, your greater than, less than sign, and turn it into an arrow like that. And so it's pointing towards the products. This wouldn't be applicable here. And then here, I would say A is in equilibrium with B, but I would have the greater than sign pointing the other way, like this. And so what that means is the reaction is going less than 50% forward. So it must be favoring the reactants. Or what I can do is I can take that and turn it into an arrowhead. And because it's pointing at the reactants, I know I have more reactants. So these, along with the equilibrium expressions, are all of the ways that we can express where the equilibrium is in terms of the amount of products and the amount of reactants we have. Lastly, what we're going to do is we're going to look at two reactions, one favoring the products and one favoring the reactants. So what I'm going to do is the first one with you. We're going to start by writing the expression. So it's the most common way of expressing it. We have an equilibrium. So I'm going to start with this. K is equal to, I highlight all the states. Everything is fine to be there. Then I take the concentration of my product, which is NO, and I raise it to the power of its coefficient 2. And then that's all over the concentration of the reactants raised to their powers. And this is multiplication, it's not addition. This is the product of the reactants. So there's my expression. And then I notice that this K value is extremely small. This reaction essentially does not happen. 10 to the negative 31 is an astronomically small number. Now this is good for us because if nitrogen and oxygen, which make up basically all of our atmosphere, reacted like this to produce nitrogen monoxide in high concentrations, we would just all be dead because nitrogen monoxide is so poisonous. The next thing I'm going to do is I'm just going to express this in a bunch of different ways. So I know that the K is less than 1, which is telling me that my reactants are favored, or that I have a greater amount of reactants than I have products. And that if I was to write above this equilibrium sign here, a sign for greater than or less than 50%, I would write less than 50% forward. So now what I would like you to do is the same idea for this one here. I want you to write down its expression. Is the K greater than, less than 1? Products or reactants favored, etc. Pause the video now and give the question a try. Now that you've had the opportunity to try the question, let's go through it. So the first thing I would do is I'd highlight all the states, cross out any that don't belong. This is a homogeneous gaseous mixture, nothing gets canceled out. And then I'm going to underline my coefficients. They're all raised to the power of 1, so that makes it nice and easy. K is equal to the concentration of my product, PCl5, raised to a coefficient of 1, all over PCl3 raised to its coefficient 1 times Cl2 raised to the coefficient of 1. So there's my mass law expression or equilibrium expression. And then I'm going to focus on the K value. The K value here is 5,000. That's much bigger than 1. So I can say K is greater than 1. Or I can say that the products are favored. Or I could say I have more products than I have reactants. Or above this symbol, I can have a greater than or less than 50% forward reaction symbol. And so it would be greater than 50% forward, and it would be pointing in that direction. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.